Hello, hello,
Hello. Hello.
hello everyone. Today we shall discuss about thermal properties of matter. And in thermal properties of matter, this is for class 11 CBSE. And generally we will deal with NCERT book. All the problems will deal and all the things will deal here. Now see how we are going to discuss these thermal properties of matter. First of all, we will do about know about the unseen architecture of heat. You see here that what is that understanding the thermal properties of matter and how they shape our world. You can see here the unseen architecture of heat, understanding the thermal properties of matter and how they shape our world. Now we learn various things about heat and temperature. The word heat and temperature is something different from one another. First of all, you have to learn what is temperature, what is heat. That you will learn. Only then you can understand the other various things. Right? First of all, we learn what is the meaning of temperature and heat. First of all, you have to remember that heat is a form of energy. Right? Heat is a form of energy. And what is temperature? Temperature is a property of the substance by which it says the thermal conditions of a body. Now we see there is the thermal conditions of a body. Now we can see here that these are the next one is we have all seen it, but can you explain it? The blacksmith trick. Why is an iron ring heated before it's fitted onto the rim of a wooden wheel? Why we do this one? These are some of the questions we are asking before going into the chapter. And the name next one is the coastal clockwork. Why does the wind at the beach often reverse direction after the sun goes down? These are the few questions we deal with heat and temperature. The boiling point plateau. Why does water's temperature stop rising at 100 degrees centigrade no matter how much more you heat it? These are some of the questions we are going to deal with it. Now you'll find beside that there are various other things we can do that these are the features we have to do. Why we should. These are the few questions asking and how we can solve this question. If we go into details, it all begins with a difference in temperature. And all this is the difference of temperature. Temperature, a relative measure of the hotness or coldness of a body, it's an indication of kinetic energy, not energy itself. And what is heat? I already told you that heat is a form of energy, a form of energy that is transferred between systems because of a temperature difference. Heat flows from hotter to colder objects, right? And there is another word what we are going to deal with it is thermal equilibrium. Thermal equilibrium. In thermal equilibrium, this transfer continues until the body and its surroundings reach the same temperature. Now going to the next phase that what we are going to do is this one. Establishing a common language for hot and cold. What it means. You see here, thermometers rely on physical properties that change with temperature, like the volume of a liquid. To create a scale, we need two fixed reference points, the freezing point, or we call it as ice point, and boiling point or steam point of pure water. Celsius scale sets the ice point at 0 degree centigrade and the steam point at 100 degree centigrade, and there are 100 intervals. Fahrenheit scale sets the ice point at 32 degree Fahrenheit and the steam point at 212 degree Fahrenheit, and that is 180 intervals. Now, now we want to make much other difference also and see what are the other differences here. And every day there will be a online class on class physics at this time, that is from 6:30 to 7:30. This is our timing of online class. Every day we'll get this type of class, right? Next, you see, this we are going to discuss with this one, that this temperature scale, that is in Celsius, it is 0 degree centigrade. This is the ice point. This is steam point. And Fahrenheit scale, it is 32 degree Fahrenheit. And it is 212 degree Fahrenheit. Besides that, there are other scales also, that is Kelvin. And you know that the SI unit of temperature is Kelvin. And in that case also, you see that there are 2 points. One is known as the ice point and steam point. The ice point is represented here as 273 Kelvin, 273 Kelvin, and the boiling point or steam point is represented as 373 Kelvin. These are the three scales: centigrade, Fahrenheit, and Kelvin. Besides that, you have to know what is the relation between these centigrade, Fahrenheit, and Kelvin scale. If you want to find the relation can be found out by this formula, that is name of the scale minus C minus the ice point, that is 0. And you see how many number of divisions, that are 100 division here, right, in case of centigrade. And in case of Fahrenheit, you see 212 minus 32, this is 180 division. And in case of Kelvin, it is also 100 division. Now we'll find a relation between the three, that is centigrade, Fahrenheit, and this Kelvin. What is the relation? Relation is C minus 0 divided by number of division, 100, is equal to name of scale is Fahrenheit, minus ice point is 32, 32 divided by how many divisions are there? 180 divisions. 180 divisions is equal to K minus what is the ice point? 273. 273 divided by how many divisions are there? 100. This is the relation between centigrade, Fahrenheit, and Kelvin. You can convert from centigrade to Kelvin or centigrade to Fahrenheit and Fahrenheit to Kelvin at the same time. These are the various ways, and every day we are going to take in online class, right? Now you see, this is the relation between centigrade, Fahrenheit, and Kelvin scale. Besides that, we'll go to the next session, that is this one, or you can write in this way also, that is TA. If you want to find this one, this relation is the same. TA, temperature in Fahrenheit minus 32 by 180 equal to TC by 100 or C by 100, same thing, right? And if you want to relate with Kelvin, this is the formula to relate. You can convert this formula by Centigrade to Fahrenheit, centigrade to Kelvin, Kelvin to Fahrenheit, Fahrenheit to centigrade by using this formula, right? Now you can do another thing also. These are the things. Next one, what we're going to discuss is this one. What are strange and vital anomaly? This is very much important for us because we know that most substances expand when heated, but water behaves differently. What is that? Between 0 degree centigrade and 4 degree centigrade, water contracts on heating. This is very much important. That water contracts on heating. How it goes, that I'm going to show you also, that how it contracts. This is the between 0 degree centigrade and 4 degree centigrade, water contracts on heating. Now I see that, and water contracts on heating. Now we see that what is strange and vital anomaly. What is this one? This is what we call it as anomalous behavior of water. This is called as anomalous anomalous behavior of water. You see, this is known as anomalous behavior of water because water is something behavior of water. What is something different from other elements or other compound? You see, these most substances expand when heated, but water behaves differently. Between 0 degree centigrade and 4 degree centigrade, water contracts on heating. You see here, the volume of 1 kg of water. It's 0 degree centigrade, the volume is here. And whenever any increasing the temperature, the volume contracts and contracts up to here at 4 degree centigrade. After that, it again rises. This is the anomalous behavior of water. And you know that density equal to mass by volume. Density equal to mass by volume. What it means? It means that volume is inversely proportional to density. Volume is decreasing, that means density is increasing. At 4 degrees centigrade, the density is maximum in case of water. See here, this is the density. This value is the density of water at 4 degree centigrade, maximum density. After that, it will decrease again. After 4 degrees centigrade, it will decrease. Maximum density of water is highest at 4 degrees centigrade. Now, this means water reaches its maximum density at 4 degrees centigrade, right? And what is the environmental effect? There are many environmental effects you find here. That is environmental impact. What is that? As a lake cools, the 4 degrees centigrade water densest sinks. Water colder than 4 degrees centigrade is less dense. Water colder than 4 degrees centigrade is less dense and stays at the surface where it freezes first. This insulates the water below, protecting aquatic life. You see here this one. Suppose this is the pond. This is the pond. You see here this one. This one is the minimum value. It is at 4 degrees centigrade. After that, it will be the less dense, that is 3 degrees centigrade. After that, it is 2 degrees centigrade. After that, it is 1 degree centigrade. 1 degree centigrade. After that, it is 0 degree centigrade. And at 0 degree centigrade, this part will freezes to ice. But this is water. It is protecting the aquatic life of aquatic life. So in this way, we get water's strange behavior. Besides, there are other factors also that water is something different from other liquid. Some properties are there. The number one is this one that water reaches maximum density, that the density of water is maximum at 4 degrees centigrade. This is one property. There is another property also. The specific heat of water is maximum, is much more than any other liquid. The specific heat of water, the specific heat of water is more than other liquid, more than other liquid. There are other factors also. That is, water has the property of capillarity. What is the property of capillarity? What is the property of capillarity? What is capillarity? Capillary. That means if we take water in a glass of water, see the surface of water. If we take what is capillary? Capillary is a tube of a small radius. The water will rise up to some from here. This is the capillary property of water. Capillary. This is what is capillary. So water is something different from other liquid. And water behaves, you see, vital anomalies there. Water is strange and this for this, the protecting the aquatic life. It protects the aquatic life. Right? Now we're going to another one. That is, this is the what is strange and vital anomaly. I already told you there are three factors. The specific heat of water is maximum than other liquid, and the maximum density is at 4 degrees centigrade. And this means water reaches its maximum. These or between 0 degrees centigrade and 4 degrees centigrade, water contracts on heating. This is very much important. And it has a property of capillarity also. These are the few strange factors which are different from other liquids. Now, if you go to another one, now a substance resistance to temperature change. This is also very important. A temperature resistance, temperature a substance resistance to temperature change. Now we'll go to this one. A substance resistance to change to temperature change. What is that? A specific heat capacity. You have to learn the term word. What is the meaning of a specific heat capacity? A specific heat capacity is the amount of heat per unit mass required to change a substance temperature by 1 unit joule per kg per Kelvin. Therefore, del Q is equal to ms del T. ms del T. What is the meaning? Del Q is change in heat. M is the mass. S is specific heat capacity, and del T is the change in temperature. A substance with high specific heat capacity heats up slowly and cools down slowly. Inside, water has one of the highest specific heat capacities, making it an excellent coolant, car radiators, and heat retainers, hot water bags. I already told you. The a substance with high specific capacity heats up slowly and cools down slowly also. Here you can see that 1 kg of water has heat capacity nearly 4186.0 joule per kg per Kelvin. And in the case of 1 kg of aluminum, it is only 900 joule per kg per Kelvin. So you have to learn all these things in thermal properties of matter. Now we are going to another important phase, that is this one, the hidden energy of changing state. This is also very much important to know. When a substance changes state, that is solid to liquid, liquid to gas, its temperature remains constant, even though heat is being supplied. This energy is called the latent heat. It's used to break molecular bonds, not to increase kinetic energy. There are two types of fuse latent heat. One is latent heat of fusion for melting or freezing, and latent heat of vaporization for boiling or condensation. There are two types, and the formula for that is Q equal to ml. Q is quantity of heat, m is the mass, L is the latent heat. And you see in this graph, you see this one, the graph 0 degree, 50 degree, 100 degrees centigrade. These they were when warming eyes at 0 degree centigrade it melts, and in this phase you will get two state, both solid and liquid. And after being it is changes at this period totally liquid. After that, water is again warming. After that, it goes to 100 degrees centigrade, and in 100 centigrade, you will get two phase. That is, you will get liquid plus gas in this period. After that, it totally changes to steam. In this way, heating curve for water arise. Besides that, you'll get another thing, that is there is another question. Why steam burn is more severe than a burn from boiling water? Why? That is the question. Question is why this question arises, that why is steam burn more severe than a burn from boiling water? You can see here that the latent heat of evaporation for water is 22.6 into 10 to the 5 joule per kg. This is latent heat of evaporation. This means 1 kg of steam at 100 degrees centigrade contains 2.26 million joules more energy than 1 kg of water at the same temperature due to water of vaporization. We are getting 2.26 million joules more energy than 1 kg. So when steam condenses on skin, it releases this massive amount of latent heat before it even brings to cool down as hot water. So this is the way answer why a steam burn is more severe than a burn of boiling water. And the next thing we are going to discuss is this one, that is question number 4. Three ways heat gets from here to there. What is the meaning is that there are three ways heat can be transferred. One is known as conduction, that is heat transferred through direct molecular collisions dominant in solids. Convection, heat transfer by the bulk motion of fluids, liquids, and gases. Radiation, heat transfer via electromagnetic waves, requires no medium. That is the sun. This is our earth. The light from the sun comes to our earth by the process of radiation. There is no medium. Up to here it is here. After there it is vacuum. So there is no medium here. And in case of conduction, it is the heat is transferred by the molecular collisions. The molecules here vibrate in their position. One, two, three, four. These first molecule transfer the heat energy to the second molecule. Second molecule transfer the energy to the third molecule. And third molecule transfer the heat energy to the fourth molecule. In this way, the heat is transferred from A to B. It is by touch. But in the case of convection, you see, if we heat a water in a beaker, this is water. What happens in this case? If first the water near this surface will heat it up, and water being molecule is heated up, it goes up, and the heavier molecules comes down, goes up and comes down. In this way, water will circulate in this way and heat it. If you give some sawdust, you can see that sawdust are revolving in this direction, revolving in this direction. That means convection is for liquids and gases, and it is revolving in this direction, right? Revolving. That means what? That means it is the heat is transferred by the actual movement of material, actual movement of material, actual movement of molecules, of material, movement of molecules. But in the case of conduction, only one particle is giving the energy to the next particle. And in case of radiation, there will be no medium and it's transferred by electromagnetic waves. We know that light is an electromagnetic waves. So we learned about the conduction, convection, and radiation. After that, we'll get to another section, that is this one. You see here, this one is some materials are highways for heat, others are roadblocks. The rate of heat conduction is described by the formula H equal to K Tc minus Td by L. This is the formula for rate of heat conduction. Thermal conductivity K is a measure of how well a material conducts heat. High K means good conductor and low K means insulator, that is wood and air. Thermal conductivity can be written as logarithmic scale in this way, that silver is 406 watt per meter per Kelvin. Steel, this is wood, this is air. This is why a brass tumbler K109 feels much colder than a wooden tray on chilly day. The brass is heat highway, rapidly conducting heat away from your hand. So these are the various features of conduction of heat. And we remember this from the rate of heat conduction described by this. And K is known as the thermal conductivity. And this is a constant also. Thermal, this is a constant value. It is a particular value. It is not variable. Now we're going to learn another thing, that is this one, that is mystery solved. Now the whatever we learned is the mystery solved. We have fixed some questions and the questions will be answered now because we got all the answers. To create an incredibly tight fit between an iron ring and wooden wheel, that is in thermal expansion. The same radius, near the same radius, it fits here because when you hit this one, it will expand a little. After that, it fits here. Massive compressive force it will fit, and you after cooling, it fits here. What is the process? The ring is forged with a slightly small diameter, slightly small, 5.231 is 5.243, small diameter. The ring is forged with a slightly small diameter, then heated. Iron's high coefficient of linear expansion alpha A causes it to expand enough to slip over the wheel. The result, as the ring cools, it attempts to contract. The rigid wheel prevents this, creating immense compressive force known as thermal stress, locking the assembly together. For example, this one, to fit a 5.243 meter wheel, a 5.231 meter iron ring must be heated from 27 degrees centigrade to 218 degrees centigrade. In this way, this is solved. And the next one is what is say is mystery solved. This one also. The reversing sea breeze. I already told you that in case of land heats up much faster than water. Here above the hot water rises. This water rises and cool water comes from sea to the land. This is known as sea breeze. From sea to land, sea breeze. This water rises up and this is also one type of convection. And the sea breeze, that is the water from ocean to land, it flows. Cooler, denser air from the sea flowed inside inland to replace it. That means sea breeze. The water air flows from sea to the land. This is during daytime. But at night time, what happens? You see, land cools quickly, water cools slowly. So this sea now warmer, air rises above it. Air rises, and these the air from the land goes to the sea. This is land to water, land bridge. Sea bridge, sea to land, sea bridge, land bridge. This flows in this direction. And this is also one type of convection. This is the reversing sea bridge I already explained. Now, we're going to the next session that the mystery solve the boiling point plateau. Water's temperature rises until it reaches 100 degrees centigrade. Then it stays at 100 degrees centigrade as it boils away. The tool, change of state and latent heat of vaporization. Explanation. At the boiling point, all added heat is used for the phase change. It supplies the latent heat needed to break intermolecular bonds and convert liquid water into gaseous system instead of increasing the water's temperature. Conclusion, temperature cannot rise again until all the liquid has turned into vapor. All energy added here is consumed as latent heat to change its state from liquid to gas, and in this case, boiling or phase change. So, this is the answer of the previous question. From black experience to planetary climate, heat is shaping our world. In this case, you see what is signaled. The principles of thermal expansion, specific heat, and heat transfer are not just textbook concepts. They are the invisible rules that govern engineering design, natural phenomena from wind patterns to ocean currents, and even the way life survives. Understanding these dense properties gives us the power to explain, predict, and engineer the world around us. Right? In this way, we have explained all the things of thermal properties of matter. Now I'll explain one other thing that is left, that is the last thing that we want to discuss is this one. That is this phase we have left, this one. The substance resistance. I already told this one. Yes, we have finished all the chapters, right? So is there anything left? Let us see. Linear expansion. This one is left, and let us see what is the linear expansion here. You can see here that matter expands when heated. The increase in the dimensions of a body due to an increase in its temperature is called thermal expansion. Linear expansion, the fractional change in length del L by L is proportional to the change in temperature. That is del L by L equal to alpha L del T. The coefficient of linear expansion alpha L is a key property of a material. Metals generally have high coefficients. Here you can see this is copper, this is Pyrex glass, identical initial length. Copper alpha is 1.17 to minus 5 per Kelvin, expands about 5 times more than Pyrex glass alpha G or alpha L 0.32 10 to the minus 5 per Kelvin for the same temperature change. Yes, you see that the Pyrex glass, that the copper expands more than that of Pyrex glass. Copper expands more than that of Pyrex glass, right? So the is known as thermal, and this is known as coefficient of linear expansion of solids. And there are three expansion later on we will discuss. That is alpha is known as the coefficient of linear expansion, If we say beta, that is coefficient of area expansion, and coefficient of volume expansion is gamma. And there is a relation between alpha, beta, and gamma. That is alpha by 1 is equal to beta by 2 is equal to gamma by 3. That's all. And our next class will be tomorrow at 6:30 a.m. Every day we will take a online class at 6:30 a.m. every day. Thank you everybody for watching this video.